Alright, let's review Unit 7. So, Unit 7, rotational energy and momentum, is actually not like a long unit. Like, there's not a lot of content. It's really about just practicing. It's just really about getting a lot of practice in, because it's not a lot of concepts, but it's like there's a lot you can do with them, and there's a lot of different types of questions they can ask. So I'll definitely talk about some of the key points, all the key concepts, what kind of problems you could face, but practice goes a long way for this unit. So let's just get started in talking about rotational energy. Like what is rotational energy? We got introduced to rotational energy with the Kit Kat. Not Kit Kat, I don't know why I said Kit Kat. Tic Tac. So if we had that Tic Tac, right, it went on that path. Sometimes it would bounce this high, and then other times it would bounce a little bit higher, and then it had all sorts of weird bounces, right? And we weren't sure why. It looked like it broke conservation of energy, right? How can it have more UG than it started with right here? The truth for that was actually rotational energy. So initially, maybe the Tic Tac didn't start with much rotational energy, but what as we noticed is on the second bounce, it was spinning really fast, right, with a really high omega. And then on the second bounce, it wasn't spinning as fast. But then on that third bounce, maybe it was spinning really fast again. So definitely something going on with the spinning and its height. It seemed like high spinning led to a low height after the jump. So we kind of investigated that, and we determined that there is such thing as rotational energy stored rotationally. So for this Kit Kat, right? I don't know why I said Kit Kat. Tic Tac. Its total kinetic energy through each bounce, like let's say like right here, right? Like this is where it's all kinetic. The total kinetic energy is still the same, right? UG turns into K, UG turns into K, UG turns into K. What's happening is that the total kinetic energy, right, that this Kit Kat has is being stored as K rotational, as well as its regular K, like it's K linear, K translational. So if it's all UG right here, and then right before the bounce, it's all K, afterwards, the ground creates a torque on the Tic Tac, and that gives it some K rotational. And then that K rotational is constant. It has, so right now, maybe if 3/4 if the total energy was K rotational, for the entirety, it's going to be 3/4 K rotational. There is no outside torque in the air that'll change its rotational energy. That's why, if it's 3/4 K rotational, only 1/4 is going to be UG, and that's why its height is so low. But then afterwards, maybe it loses K rotational, so it's only 1/2 K rotational for the total energy. So then at the top, it's going to have more UG because that K rotational didn't change. Only the K linear transformed in a UG. So that was kind of a big idea as well, the idea that K rotational only changes with the torque. There is such thing as, I think there's such thing as angular work. Like we learned about linear work, there's angular work. You don't really need to understand that or really know what that is. Just remember that torque changes K rotational, so without a torque, your K rotational is constant. So the equation, the general equation for K rotational is, it's K rotational is equal to 1/2 I omega squared. And if you're like, that seems kind of familiar, a 1/2 and a squared, well, that's exactly what K linear looks like. K linear is just 1/2 mv squared. So instead of velocity, we have rotational velocity. Instead of mass, we have like rotational mass, rotational inertia. The 1/2 stays, and it's a nice reflection of our original K linear equation. There's a lot you can do with this equation, and there are all sorts of like conservation of energy equations you can apply. Just like energy, conservation of energy applies, and we can use that to solve problems. So let's take a look at a sphere rolling down the ramp. Okay, so we have a sphere, height here. They don't actually matter, but let's just say it starts at a height, and we got to figure out its speed at the bottom, right? It starts at rest, and this has a rotational inertia of 2/5 mr squared. I'm just going to go over like an example of using conservation of energy in a case like this. We know that all the energy initial is going to equal the energy final. If we include everything in our system, the ramp, the sphere, everything, the earth, we know that there's no outside forces doing work. So, really, what we can say is that, well, all the energy is going to be UG. And then at the bottom, it's going to be moving, so there's going to be K linear. There's also going to be that K rotational, right? It's going to roll without slipping, so it's going to have that K rotational as well. Awesome. So UG equals K linear plus K rotational. We can just now start substituting the equation that mgh equals 1/2 mv squared plus 1/2 I omega squared, and then we can expand that I, right, the rotational inertia, for 2/5 mr squared. So take a look, right? We have the 1/2 from the original equation. We still keep that 1/2. We have to add in that 2/5 for substituting an I, 2/5 mr squared. All right, so the m's, actually, I'll cancel. I know there's a big M, little m, that's just a mistake. They should have all the same mass because it's the sphere rotating after all, so it's all the same m. We can cancel out the m, and then there's this r, right? There's this like r. What we can actually do, it's kind of pretty cool, is, well, we want speed. We don't know what omega is. We can just use the bridge equation, right? Because it's rolling without slipping. We can do v squared over r squared, right? If you do v over r squared, v squared over r squared, cancel out the r squared, you're really left with gh equals 1/2 v squared plus 1/2 times 2/5, that's 1/5. And then mr squared is all canceled out. We just get 1/5 v squared, which is the same. If you do the fraction math, 1/2 v squared plus 1/5 v squared is 7/10 v squared. And then what you'll get is the total speed is going to be square root 10/7 gh. And that's like a derived equation, but there you go. You could do it with just conservation of energy. With torque, you would have to think about, okay, well, there's force friction, there's going to be, there's the angle, you got to think about, you got to use linear acceleration because there's the two unknowns. It's a mess, but energy makes it a lot simple. So just like how linear energy makes things simple, so does rotational energy. That's just one of the types of problems I can go over, but there's all sorts of energy problems. So there's stuff with like pulleys, right? You have your pulley here, mass, and then you got to figure out like what's the speed of this mass, right? You would do the same steps with conservation of energy. It starts all as UG. Once it goes to a certain height, it transforms into K linear and K rotational. And then just a side note, right, you can use the bridge equation. This omega is going to be the same as V over R, where V is the speed of the falling mass and radius is the radius of the pulley. The bridge equation works because there's that rope that doesn't slip. Everything works out the same. So there's all sorts of different types of rotational energy problems. To be honest, rotational energy, like, it's not much we learn. We don't learn angular work. It's really just doing conservation of energy a bunch of times. And sometimes the problems can get hard. That's why practice is really important, but I always start with just thinking about what is E initial and then what is E final. I want to also talk about energy graphs. Those can be a pain in the butt sometimes. I'll walk through one pretty quickly because I know this was on, I'm actually not going to say that because I might get in trouble, but this was a problem I saw where you had like this ramp, right, flat edge, no friction, and then there was like this sort of spot where you can like there's this there's like this little spot here. So let's think about where you can fall. Think about like rotation versus distance, the distance traveled. So if we're doing energy versus distance, and then you can always do energy versus time. Those stuff get complicated, and I'll leave that out. I wish I didn't rush the energy video, but I'll leave that here. Let's say call this point A, point B, point C, and then point D. So from A to B, it's gaining K rotational, right? So it's gaining some K rotational. I drew this as straight because remember, it's the distance it's falling, so there's going to be UG, right? And then the UG changes at a constant rate because each distance it travels, it falls the same height. There's like that, it's like a straight ramp, so everything's constant there. It's going to be a straight K rotational graph. From B to C, so let's call this A, let's call this B. From B to C, there's no torque, so obviously its K rotational stays the same. And then from C to D, it's going to keep its rotational energy. It's not going to lose any rotational energy from C to D, so we can do the same sort of straight edge there. There's no torque that'll change its K rotational. This is all, yeah, K rotational. For K linear, it's very much the same, right? It's going to be straight from A to B, maybe a little bit more, maybe a little bit less. We don't really know, and we'll actually talk about, you know, how to know which one's more or less, you know, because there could be more K rotational. We don't know, just based off the scenario. So we'll say K linear, and then same thing here from B to C, you know. But remember, from C to D, their gravity, like the UG, I should say, the UG. This is kind of where people mess up a lot. People think, okay, from C to D, obviously UG is transforming. It should be straight. It shouldn't be straight because from each distance, we're not doing height, we're doing energy versus distance. If this was energy versus height, yeah, 100%, this should be straight. But for each distance this thing falls, it's falling a different and different height. It's falling a little bit more. I'll explain that more in detail, like maybe if you ask me, because it's kind of hard to explain. But I think that's kind of the gist. Like each distance it falls on its path, it falls, like its height changes more and more, which is why you actually get a curve. And then you can reflect this same exact graph for UG, right? Instead of, you just do it now, everything sort of opposite. So yeah, there you go. That's kind of how energy graphs work, and it's just thinking through them. The big key thing here is that K rotational does not like change in the air if there's no outside torque. Excuse me, but now that's kind of it for K rotational. One last thing I'll just kind of add is just talking about this idea of, you know, if you had a hoop versus, you know, if you had a hoop versus like a solid hoop or a disc or whatever, we have to figure out what is going to win the race if they both start at the same height. We know that, well, from Unit 6, we know that the solid disc is going to win because it has less rotational inertia, so it's easier to angularly accelerate. So it's gonna win, and it's gonna be moving faster at the bottom. So because it's moving faster at the bottom, they both have the same mass. Let's just say that they both have the same UG because they both start from the same height. If the solid disk is moving faster, it has more K linear compared to the other disk. And let me actually draw this out. The hollow, or the hoop, so everything is UG. For the hoop, it has less K linear than the disk. The K linear is more for the disk because it's moving faster, which is kind of counterintuitive, but now the disk, or the hoop, has more K rotational. And that's kind of counterintuitive because it's like the hoop has more rotational inertia. It should be harder to angularly accelerate, but it has more K rotational. Now for the full-on explanation of like the way that everything balances out with like the difference in I and the difference in omega, it is a bit, it's actually probably a bit complicated. The idea here is though, is that we could use conservation of energy to basically confirm that yes, this does have more K rotational because it has less K linear. Like it has to, it's kind of that kind of thing. The full explanation on why is more like a Unit 6 thing, and has more to do with torque, and maybe I'll talk about that more because it's complicated, but I just wanted to talk about like the fraction of K rotation versus K linear, and you can derive the math for that. But in terms of rotational energy, that's kind of it. Let me just check how much time I'm at. Okay, 14 minutes, not bad. Let's talk about angular momentum. So, angular momentum is pretty cool stuff. Let's let's say you're on like a frictionless chair, right? You're just on a frictionless chair and you're not rotating initially. What do you need in order to start rotating? Well, you're gonna need a net torque, right? Because you need an alpha. You need an angular acceleration from a net torque in order to get you spinning. So, that makes sense. Net torque causes angular acceleration. But for a classic move of like the ice skater pulling her arms in order to spin faster, is there a net torque on her? No, because you can't apply a net torque on yourself. You can't apply a force on yourself. You can't apply a net torque on yourself. So how is that possible? How can she speed up her angular velocity without any net torque? Because there isn't an angular acceleration. There 100% is an angular acceleration, but how? Without a net torque, how is that possible? So what this problem makes us realize is that just by observation, T net equal to I alpha is not always true. This isn't always a true case. Not for every scenario, because obviously as an ice skater pulls her arms in, there's sort of that sort of contradiction where it doesn't really work. There's zero net torque should result in zero alpha, and just because decreasing her inertia, because that's what she did, she decreased her rotational inertia, that won't automatically increase angular acceleration. Like, that's not how it works, because this term is zero. If you decrease that, it's still all zero. So there can't be any angular acceleration. So this introduces the idea of angular momentum. Angular momentum, just like sort of linear momentum, it's how much rotational oomph an object has. It's really defined, so L is actually the variable for angular momentum. It's defined as the rotational inertia of the spinning object times its rotational velocity. So, if there's no net torque, just like so, let's actually take a look, right? T net equals I alpha. I know I said this isn't valid, but I'm gonna just give me. I'll talk about that. Torque net equals I alpha. This is torque net. This is the same thing. I'm just going to do some algebraic manipulation. Alpha is the same thing as your change in omega over your change in time, right? Omega over time. Now, if we multiply both sides by time, you get torque net times time is going to equal I times your change in omega. So, torque net. So basically what we got is that I times change in omega, that's your change in angular momentum, is equal to, and that's equal to torque net times time. This is very similar to F net times time equals M times change in V. However, what this equation doesn't consider is that objects can change their rotational inertia. This equation is not true whenever an object changes its rotational inertia. Don't try to use this for this kind of a scenario. Use it for something like a sphere. A sphere has a fixed rotational inertia. You can use that then. But in this kind of case, it actually doesn't equate. Now, torque net times time will lead to a change in angular momentum. But instead of I times change in omega, your I can change. So really, it's change in I times omega, right? Like, you can change your I. So this is the same thing as torque net times time equals your change in L. So if there's no net torque, your change in I omega is a constant. Like, it's zero. So that means that I final omega final minus I initial omega initial equals 0. Therefore, I final omega final is then equal I initial times omega initial. So basically what we're saying is that, hey, if there's no net torque, the initial angular momentum is going to equal the final angular momentum. And we can change our I. So if our I decreases, in order for this to equal like the same value, in order for angular momentum to be conserved, because that's what we're doing, L final equals L initial, if I goes down, your omega has to go up. And there are some other physical causes at play with like forces and stuff that are actually like resulting in this change. But what we're worrying about is just we know the omega must go up because the I decreases. That's kind of conservation of angular momentum there. So no net torque, angular momentum is conserved. For a lot of problems, angular momentum is actually conserved. There's not a lot of problems where you will do like angular impulse, but that formula is still there. Torque net times time equals change in I omega. So let's go over some examples of angular momentum problems. So a common one, and once again, there are so many variations of these problems. I'm only going to really talk about a few. I would love if you could just practice. Like that's how you're going to really improve a lot in this unit. Let's say we have a disk, right? And it has a mass, and it's 1/2 mr squared for its rotational inertia. And then it has a mass of m and a radius of r, and it's initially spinning with a certain angular velocity, and we're gonna drop in at rest, initially not spinning, but we're gonna drop in a disk that is 4 times the mass. So this is 4m, and then it's the same equation. After we drop it, everything spins together. So they all spin together. And let's say we want to figure out what is a final omega in terms of the initial omega. So what we would do is we would say for the whole system, for the 2 disks, angular momentum is conserved. There's no net torque. So I'm going to say, hey, L initial is just going to equal L final. So I'm going to do, I'm going to say that the L initially the only thing spinning in our system is going to be that 1/2 mr squared object with the mass of m. I don't know why I said it like that, just the disk. So we're going to say, hey, I omega is going to equal, so I'll say I1, so this is 1, 2, I1 omega initial is going to equal, they're both rotating as one object, so we can treat it as like adding up the rotational inertias, I initial plus, or I1 plus I2 times omega final. And then what I can do is I can do, okay, I initial is, or I1 is 1/2 mr squared. Omega initial is going to equal 1/2 mr squared plus 1/2 4m r squared omega final. So then I can add these two terms because they're the same radius and same, 1/2. This will be 1/2 5m. So 1/2 5m r squared, and then we can clean this up a little bit. Then hey, take a look. The m's all cancel out. The 1/2 cancels out. The r cancels out. You're really left with omega initial is going to be 1/5 omega final, or 5 times omega initial will get you omega final. Wait, that doesn't make sense. Oh yes, because I have to divide by 5. So it's 5 omega is equal to 5 omega final, or omega initial, or 1/5 omega initial is equal to omega final. So it has 1/5 the rotational speed afterwards. That's really one out of the many, many kinds of rotational momentum problems. One thing I also want to talk about is also like the graphs, right? If you're doing angular momentum versus time, for the whole system, it's constant. Like we just kind of did that mathematically, so there's no net torque. It's going to be constant for the whole system. For one of the disks, the angular momentum is going to decrease, right? Because initially it's spinning with omega initial, and then it's going to be spinning with 1/5. So it's going to be initially with the high angular momentum. Actually, we'll say it's going to be all of this, right? Because all the angular momentum initially is stored, not stored, but is in the first disk. It's going to lose a lot of its angular momentum when the second disk drops on. In order for angular momentum to be conserved, this second disk is going to start with 0, and then for angular momentum to be conserved, it's going to have an equal and opposite increase. Right? It needs that equal and opposite for angular momentum to be conserved, so that the whole is still the same amount. So one type of angular momentum problem There's a lot of them, and I would really recommend doing some practice with stuff like merry-go-rounds. Like, I could talk ages about the different kinds of problems. It's really just this key concept of conservation of angular momentum. And yeah, so I would like to, I can end off with just one thing, which is the angular momentum for a linear object. So, for a linear traveling object, let's think about this for a second. We have, let's say there's a rod, and it's fixed in place by this point, okay? And I chuck my eraser at it or something, or a ball at this rod. And then afterwards, this rod is going to start spinning. So maybe afterwards, the ball is like wedged in, and then they start spinning together. Let's think about this scenario here. So there's going to be, initially, it seems like there's no angular momentum, right? I mean, this is not rotating, and this isn't moving in a straight line. It's not moving in a circle. There can't be any initial angular momentum. But then afterwards, there's spinning going on. There's omega. There's going to be angular momentum final. So it seems like angular momentum isn't conserved. That would be the case, right? If what we thought was true, but no, this ball has angular momentum. It has angular momentum about the axis here, right? And we know that it has to have angular momentum in order for things to be spinning. So what is its angular momentum, right? Let's say this is a length of L. Right as it, I don't want to do R because L is the angular momentum equation or variable. Right as it hits, right, we could still use L equals I omega. So L is going to equal I omega. For a point mass, I is just mr squared, where r is the distance from our axis of rotation. I'm going to say, write that end there, so the whole r is going to be that length. What we can do is, instead of omega, right, it's not really rotating, it's going in a straight line, we could say that omega is v over r. So then these r's cancel out, and you get L is equal to mRV, or mvr. So there you go. Now what you notice is that, okay, that makes sense. We could still do our L initial equals L final. We can do mRV is going to equal I ball plus I rod, omega final, and then we can do our calculations. But what happens if we threw the ball this way? We can imagine there won't be any spinning, right? If we think about just the rod system, the force by the ball is parallel to the displacement. If we think about torque, that won't cause any, and that won't lead to any torque. So, how, like angles, how do we, well, I just gotta, first of all, check my camera. I just want to make sure everything's in frame, because oh yeah, everything's fine. How do angles come into play, right? You can imagine if I did it at an angle, if I threw it at an angle, it wouldn't be spinning as fast. Just intuitively, that kind of makes sense. So, this is where we only worry, if this is velocity and this is velocity, for angular momentum, we only worry about the perpendicular axis, or the perpendicular component. And so we would tack on, right, if we think about the angle in between, we would add on that sine theta for those angled launches. Angular momentum is not torque. I know there is a sine theta, but angular momentum does not cause a torque, right? Like angular momentum is its own thing, separate from torque. Don't confuse this with torque. It's just another case where only the perpendicular velocity contributes to the angular momentum. So yeah, that's really all of Unit 7. I went through the packet, and I think that's kind of everything. What I would do is just practice a lot of the problems, get used to a lot of the problems, right? Like if you have a problem with an orbit, like Halley's Comet, right? Remember, the linear momentum is not conserved because there's that outside FG, but the torque, or the angular momentum is conserved because the entire time the force is parallel with the radius, the lever arm. So there's no net torque, which means as it gets closer, if we think about MVR, R gets smaller, so V gets bigger, and then that's why it speeds up and then slows down. try to immerse yourself in a lot of angular momentum problems, rotational energy problems, all sorts of problems, and I think you'll be fine for this unit because it's not a lot of content, really. It's just applying these concepts in a lot of different areas. So yeah, thank you for watching. Sorry if I sound a bit tired. I honestly just I have a stomach ache, to be honest. So yeah, but thank you for watching, and good luck on studying.